Okay, I think this will be a good one. I really hadn't thought of doing this, but someone brought it up in class. They wanted to see something like this, and I think actually it's a really good idea, so I probably should have thought of it myself. But anyway, what we're going to try and do here is we're going to try to solve a 1D bar problem. One that you would typically do in a mechanics and materials class, a sophomore level class, by using a mechanics and materials approach. But we're going to use a partial differential equation approach to sort of illustrate the way a finite element code would go about solving such a problem as opposed to a mechanics and materials approach. Okay, so the problem I want to consider is kind of an interesting one. I like it because actually, in some sense, the PDE solution is arguably easier than the mechanics and materials approach. So let's look at this one. So we have a bar that's clamped at both ends and then has a uniformly distributed load on it, an axial load. Maybe it's under its own weight. Okay, we could do something like that. Actually, let's imagine it's under its own weight. And then the value of this load is rho times the cross-sectional area. No, we'll just do rho. So it's rho g. Okay? So that's our body force. Okay? So actually, I probably should have drawn it for all intents and purposes. Going this way, so it's gravity. But you guys can figure that out. All right. The interesting thing about this is not exactly easy to figure out the stresses necessarily because this is, for mechanics and materials approach, this is a statically indeterminate problem. So the way you solve for this, if you look at the free body diagram, you got two reaction forces. Let's call this point A and point B. So we have a reaction at A, a reaction at B. You got a net force on here of rho g a l, right? And if you do sum of forces, you're going to get RA plus RB equals minus rho g a l. L is the length of the beam, and it has a cross-sectional area A. So it's A has a stiffness E and a length L. Okay? So you can't uniquely solve for RA and RB. And the way you get this is you have to get that you use the statically indeterminate case that the total elongation has to be 0 because it's clamped here. So the total elongation has to go to 0. Okay? So, and since it's a distributed force, you need to go in and figure out that the strain field is what it's going to be. It's going to be a linear strain field, right? And so we want to get the total elongation is the integral from 0 to L of the strain. The strain is the stress divided by Young's modulus, which is equal to the internal force over the area times the length. And if we draw a free body diagram, it's we have to pick one side. We can do something like this. At a general point X, all right, we've got the reaction at A, and then we've got the internal force P, and then we've got the total net force of the body force, which is going to be rho g a times this length, x. And so that tells me that P is going to be equal to minus RA minus rho GAX. And so from that, I can get that the strain is going to be minus RA minus rho GAX P over AE. And I guess I could simplify this a little bit. I can get minus RA over AE minus rho G. All right. And I dropped an X. Where'd the X go? I have an X here and X there. Okay? So now I can integrate that and I can get the total elongation. It's the integral from 0 to L of the strain field minus RA over AE minus rho GX dx. And I guess technically I should have dummy limits of integration here. Oh, that's okay. It's not L. Okay, and if we perform this integral, it has to go to 0. The total elongation has to go to 0 because it's fixed on both ends. And this will give me minus RA on AE x minus rho g on 2x squared evaluated at 0 and L. That is delta, and that has to go to 0. That's the displacement condition. All right, and this will give me minus RA on AE minus rho G on 2 times L. I divide it through by L on here. Has to equal 0, and from that I can get RA. This gives me that RA is equal to minus AE on 2 rho GL. All right. Now I have one reaction force. I can use that into equilibrium. Where's equilibrium? And now I can get that RB is equal to minus rho GAL. Why do I got an E? I've got an extra E floating around somewhere. Shouldn't that E have dropped out? Yeah, this, I'm sorry. There's no E here. So, oops, excuse me. Let me just answer that phone. Okay, sorry about that. So where did I screw up? I have an extra E in here. So, there should be an E on here. Does that make sense? Yeah. And then I have an E on here. There's an E on here. There's an E on here. And then this E goes away. That gets canceled out, right? So that E goes away. The units seem right. Okay. So this is actually the reaction force. And that has units of force. That's good. Here's the reaction of B from this equilibrium is this minus RA, or that's going to be, you can see this value here is 1/2, so that's going to give me a minus. Let me do this carefully. I'm always bad with signs. Minus rho GAL minus a minus this, so that's plus rho GAL on 2, and so that gives me a plus 1/2, negative 1/2 rho GAL. So this problem actually looks like this. So we have reaction forces. These are both negative, and I guess that should have been kind of obvious. Half goes here. This is rho GAL on 2, and this is rho GAL on 2. Correct? Okay. And then we have the distributed force here. The total elongation is 0. I know that the stress at the point is this P over A. So the stress is P of X on A. P of X we got from here. That's minus RA. So that is minus RA is rho GLA on 2 minus rho GAX over A. So the stress at a point is going to be minus 1/2 rho G. Wait, I'm sorry. Yeah. It's going to be rho G L on 2 minus X. So that's the stress. And then the last one, we can get the strain. Maybe I should get another piece of paper for this. We can then get the strain. That's the stress over Young's modulus. So that gives me rho G on E, L on 2 minus X. And then finally, if I wanted to get the displacement at some point X, that equals the integral of the strain, but now we're going to use a dummy integration, so we're going to go from, we'll use chi, so we'll go from chi from 0 to chi equals to X. The strain, in terms of the dummy variable chi, d chi, and so that gives me integral from 0 to X of rho G on E, L on 2 minus chi d chi, and that gives me now rho G E L on 2 chi minus rho G E chi squared on 2. That's a chi. Right? Evaluated at 0 to X. At 0, this goes to 0, so this just gives me rho G on 2E L minus X squared. And so that's the displacement field. All right? So it's kind of good. It's not, it's one that you can solve coming out of sophomore mechanics materials, but it's not the easiest one in the world that you ever tackle because it is a statically indeterminate problem. So you have to deal with it in a little different approach. You have to use this causality term that the total elongation is 0. So you have to use that to supplement the sum of forces to give you two equations to solve the two reaction unknowns. Then you go back and you get the internal forces. Then we get the strains. And then you integrate the stresses. So that's the mechanics and materials approach. We get internal forces. From the internal forces, we get the internal stresses, P on A, MC over I. From the internal stresses, if we choose, we can use Hooke's law to get the strain, usually from something like Hooke's law. And then finally, we can integrate the strain field and get the displacement field. So that's the mechanics and materials approach. It goes in that order. Okay. Let me stop now and pause. Maybe I'll make two videos. So I'll stop here. Now I'm going to solve the same problem, but using the partial differential equations, and show you how actually finite element kind of goes the other way. Or if you do the Pde approach, you're going actually the other direction. So this is mechanics and materials goes this way. Actually, we'll show that the Pde approach, which is really kind of the same approach that the finite element method or finite element analysis uses, goes in the other direction. First, you start with the displacement, get the strain, stresses, and then the forces. Okay? Usually, we actually don't even get that. All right.